Let's finish off our look at the theory of differentiation by looking at higher derivatives of functions. Often we need to know higher derivatives of a function. For example, in physics, we know that velocity is a change in distance over time, and we also know that acceleration is a change in velocity over time, which means that the acceleration is the second derivative of the distance with respect to time. So in general, we write, for the second derivative, we just write this as d2y by dx squared. And we can think of this as the operator d by dx acting on dy by dx. And we can also write this in prime notation using 2 primes. For higher order derivatives, we can just add on another prime, so for third. And for the nth derivative, we write dy by dx to the n. And we write this as f with an n in brackets to denote the higher derivative. So really this is just about notation. Let's have a go with just a few examples. So let's find the third derivative of x cubed. F prime is 3x squared. Second derivative is then the derivative of that, which is equal to 3 times 2 times x. And then the third derivative is just 3 times 2, which is 6. So the third derivative of x cubed is 6, which is just a constant. Can we write down expressions for the nth derivative of functions? Very often we can, and actually we'll find out it's very useful when we look at Taylor series. How do we do this? Well, we do it iteratively until we spot a pattern. F prime of x is just nx to the n minus 1. So the second derivative is n into n minus 1, x to the n minus 2, the third derivative. And so in general then, if we keep differentiating until we get to the nth one, we will be left with n into n minus 1 till we get to the end of the sequence. And this is just n factorial. This is a really useful result we're going to come back to later. We can find higher derivatives for parametric equations. So dy by dx is equal to dy by dt divided by dx by dt. The second derivative of y with respect to x then is d by dx of dy by dx, which is dt by dx, d by dt of dy by dx. So in general for parametric curves it's just best to work from scratch each time. Let's have a go with the cycloid again. The second derivative d2y by dx squared, which equals a lot of stuff, and that simplifies too. Note that this is always negative, which means that the curve is always concave down. We'll come back to this and what higher derivatives mean later on.